Today we are looking at ground beams, rafts and piled foundations. So three different aspects. Before I start the program, I'm just going to run through a wee quick PowerPoint presentation. 2 minutes. Here we go, modular suite. The MasterSeries is a modular suite. What we'll be looking at is the frame analysis. We'll be looking at the frames. We will be looking at finite elements for doing our rafts. We will also be looking at concrete design for doing our ground beams, and we'll be looking at the pile cap designer. Now, if we move through to commercial software for designing beams, we have the concrete beam designer, which is a small, great little program for doing continuous beams. We can also do continuous beams using the master frame with the concrete design. This also applies to PowerPad because it has both of these programs, and the building designer suite will also have the frame analysis. So we can either do our concrete beams in the beam designers or in master frame. If they're two-dimensional, as in a grillage of beams, then we will need to use the frame analysis. But if it is just a simple continuous beam, then we could use the simple concrete beam designer. So I'm just going to come out of that and start the MasterSeries. So we do have this concrete beam designer, and I'm not going to look at that today. If you want to look at it, there's a very good video on the different aspects of designing beams that you can use. If you go into the Learning Center, it will pop up some videos for you. One of them from a wee while back was beam design, and it talks about all the different aspects of simple beam design in there, and that will give you very good guidance on the simple concrete beam designer. I'm going to look at ground beams. Now, a simple ground beam in master frame. So we're going to go into master frame and look at a simple continuous beam. Very simply, if I display the lengths, we'll see 6, 7, 7, 8, 6 meters. So a wee bit of variation there. Now if we look at our loading, we'll see that we basically have a continuous load except for this 1 point load. And if I draw some values on that for you, you'll see it's slightly big, plus the 36 kilonewtons per meter run on the loading on the continuous beam. So simple continuous beam. But the one trick that you need to know when doing concrete beams is to do with load patterning. Because this is continuous, we need to think about our load patterning. So I need to think about looking at all the spans loaded, and I then need to look at only maximum minimum. If I just increase this, decrease that, and increase that scale, there we go, maximum minimum, and back to maximum again, as you would expect. And if I then go to the third loading case, we're looking at minimum, max, min. Now you need to know why you want to do that. Why do you need to do pattern loading? And then I'll jump back as to see why we want, how we do it. So let's look at our results and our graphical results, and we look at our bending moment diagram. We get our bending moment diagram for our ultimate limit state, all spans loaded. So we have our sagging and hugging moments. So let's put on some values, and we will notice that we have here a 95 and a 203. So remember those two values, 95 sagging here and 203 here. We also have 307 at the support. Now, if I go to max min, what's going to happen is that this 95 now becomes 110. That's because there's less load here, so that this is lifting up or going down less and pushing this down. So we're getting a higher moment here than we would have got if we'd only considered maximum on all spans. The support moment is less, and if we then move to the third case, the alternate version of that, we're into minimum and maximum. So we've now gone up to 230, but again we haven't got this support moment any higher, but we're 230 in our sagging moment, whereas we were 203, which is around about 14-15% difference, an increase of around 15%. So it's always important that we do this patterning on our members. So ultimate cases, there's our pattern of loading cases for the frame. And you'll see that the support is always the all spans loaded case. So just coming back out of that, how do we do that? That's the important thing. So let's look at our loads and member loading. We're just doing a simple plain frame, one-dimensional. So we've got our loading on here. We've got two loads, a dead load and a live load with the spacing. And then we've got another dead load and a live load, and a dead load and a live load, and a dead load and a live load. But what you need to notice is that on span 1 we have D1 L1, and on span 2 we have D2 L2 and another D2, because we have this point load on here as well. And then we move to span 3 and it's back to D1 L1. What this allows us to do by alternating these loads is to go to our loading cases and say that for our loading combinations, I want the D1s and the D2s and the L1s and the L2s to be all loaded for the first loading case, so everything's loaded. But for the second case, I want to have the minimum on this span, so I've got my maximum here, but I've turned off the L2 and I've turned off the L2. So if I was to go and look at the loading at the same time and go to the second loading case, you would see maximum, minimum, maximum, minimum, maximum, because we do not have an L2. Now in the Euro code you don't pattern your permanent loads because they are permanent. If I went to the third case here, I would say it's minimum, maximum, minimum, and I just do that by simply alternating this again to be maximum on the span 2 and span 4, the even spans. So very simply we're able to do this patterning of the loads. Now I've also got the serviceability limit state loading cases in here because I wanted to have them available for foundation loading. Although, to be honest, for foundation loading, the maximum is always the all spans loaded, so you could argue that you don't need those two anyway for serviceability. These load factors are very easily set up. If I was to minimize some of these options, and I was to go to loading cases, and I was to import from another file, I could import my loading combinations from another file. Now I actually have set up some frames, and I can see that I've got these frames set up with just dead and live load, so nothing very special in here that I want to grab. There's some ground beams with the 1.25s, and here's a plain frame. So I can go and grab from another file. What I can also do is I can go in and I can go back to my program data MasterSeries, and in here I have a directory called library. And if I go into library and into loading cases, I will find that there are some finite element loading cases and some simple frame loading cases. And I don't want the attributes, if I can just minimize that bit, I'll see it's EC2 to 1.35, and that gives me my cases to bring in automatically. But it's not a difficult process to set up, and I'll just cancel all that. So very simply applying the loads. We're not learning about the loads, we're learning about the concrete design today. So let's get on and do our analysis again for our plane frame, and go straight in and into design, because we've already seen what the bending moments look like. Concrete beam design. And it's automatically come in because I've been looking at this frame before, but what we would normally get is all these options. So it would ask me, how do I want to design it? So 12s to 32s, 2 or 4 bars, covers 30 top, 50 all around the bottom, because it is going to be a ground beam. Beam curtailment will just be standard detailed, with the bars going to the supports so that we can have drop cages. Only 1 bar group per zone. That means that we don't have 220s and 225s, we just have 425s. Keep it simple. And everything else is pretty straightforward. And my design code is EC2 8666 and 500B bars and 500B links. And I just say OK. And off it will go and do the design. So what I've now got is 425s top, 420s bottom. I could probably reduce those to 16s, I can. And these are just the lap lengths for the covers required. And 3 12s. 3s and 4s don't go well together, so I'm going to say to make that 4 12s, and I'd probably actually turn around and say, well, actually it is a reasonable width. Let's get back here and make this into a 4 bar arrangement. Keep it simple, redesign the whole thing. Off it goes, and if I go out of here, we'll see that it's nearly working, and it's suggesting we may want to take action on that, but the 16s are working here. Everything else is working fine. So in this one area we're nearly working. This allows me to either come along and say, well, yeah, we will have to go up and increase. So it's left and right mouse button on the number here changes the value, and you'll see everything updates as I go. So down to 20s, pull that back to the point, and we see that we're not working. So we need to redistribute this. So what we would do is go to redistribution, and we will see that we are going to set this end to 30 and this end to 30, and just come back to the beam, and we now have the redistribution, and it now works with the 20s that we have elsewhere. So very simply, we've been able to modify our reinforcement on our beams and get it all to work. Now the other thing that I can do, although we don't have equal spans here, which makes my life a bit more awkward, is that I could take 1 kg of reinforcement and drop it on the next and the next and the next. Instead of doing that, I'm actually going to change my style. Sometimes when people are doing trying to find the right. Let's see, auto design, beam curtailment. That's it. Two-zone design is very popular when we're doing ground beams, because what it allows you, because in ground beams you quite frequently have steel that's pretty similar throughout. And if I redesign with two span beams, what we get is the first span is going to be a wee bit different, and you'll see that you get a start and then an end, and then you get a start. So lap here and lap here, and a lap here and a lap here, and obviously there's no requirements, and lap here and lap here and lap here. So I am getting a little bit here, and I am just going to take this bar and increase it. There we go. There was no real need for anything else, and then just pull that back. So we just drag the bar back. It wasn't requiring a lap because there was no in fact rebar in there that it needed, but we will just ask for one automatically and it then does it for us. So that's how simple it is to do the design of a simple beam. But normally we have more complicated structures. So what I'm going to do is I'm going to step forward and I'm going to open a recent file called ground beams plural, and this is a grillage frame, so we're definitely in master frame now, and it's got little supports, and if you look at the supports you'll see that the supports are all over the place. You're not necessarily here where you would expect it, but over here and here, maybe to cut the span down or maybe to do some other reason. We have cantilevers, and we have simply supported beams. Now, if you can imagine this beam here, this would be connected rigidly to this member and to this member. So if I look at my results, graphical, I'm going to analyze this. Don't really need horizontal load, it just comes in by default. I could analyze just as a grillage because it is a grillage frame. Look at my bending moment diagrams. What we're seeing at the moment here, when I reduce the scale and ask for a few more hatching points, is that it's come simply supported between here and here. Not with any fixed end moments. Every corner comes in simply supported. And that's how you do it if you're doing it by hand. You do every single one as a run with it simply supported. Now in reality it's fixed, but we have told it it's not fixed. Now there are two ways you can do that. And the nice thing is that the codes tell you that if you assume that it's pinned during analysis and that it's stable, that being the critical thing, then you can design it as if there's no torsion, that it's just pinned at the end, a nominal support. So how did we do that? Well, there's two ways of doing that. One way would have been to go in and pin the ends, that is, go to restraints, member end releases, and you then pin one of those two ends. You wouldn't pin both because that would give you a total instability with the support itself being pinned as well. And you can do that and walk around. Now the danger there is that you release too many and you get confused as to why you're unstable. Now the alternative way to do this, which is the way I've done it, under the analysis is under global analysis options, is I've told it to ignore torsional stiffness. So if I take out that option and say OK, and now reanalyze static analysis, you will see, again it's just a grillage, that when we look at our results, graphical, looking at the bending moments, we're going to get these kicks. You're getting a little bit of a kick around here. So you're getting a little hogging moment. Just turn off the pins. You're getting a hogging moment here, or sagging, depending on how it's working. And you're getting this member having a fixed end moment. So this fixed end moment here is going to be putting a torsion into this member. So if I look at the value of that fixed end moment, is coming in here at 35.1. If I went to the torsion, you'd see that that plus that gives you 35.1. So the torsion has been proportioned to the two sides. So as I say when I'm training, one man's moment is another man's torsion. And that is the problem that you don't want, because when we suddenly have these torsions, it's not a problem. The analysis is correct, but when we go into our concrete design, you will see when I'm in here, I'm having to put in torsional links. When I look at my results, you'll see that I've got torsional design, and I've got a reduction on my main steel and my links due to torsion. So we're removing a part of the design. So when we come into the design, we actually end up with a reduction in the areas of steel used. So now they're actually now failing in this case because of those reductions. Now clearly the designing with the torsion included is going to prevent any cracking that could occur. It's going to mean more steel, and it's also going to mean more complicated links, because the links must be what I would call a five-sided link, where you don't just join at the corner, you have to actually go round two faces to get your torsional links, and it makes that note here for them. And that's fine. Now the other method, when we did away with the torsion, so go to Analysis, Global Options, and ignore torsion, Analyze, Static, Grillage, it's happy, Results, no, Design, Concrete Design. And when we look at this member, we will see that it's all simply supported this time, and it is a lot happier, and there are no torsional links required. Now the design itself still needs to be looked after and checked out, but when you look at the results, you will see there's a wee bit of a problem with the transverse reinforcement spacings. So we need to just get another set of links in there in this case, because of this gap that we're having too big. But other than that, the design itself, sorry about that, is perfectly adequate. Now obviously we cannot use this method of releasing the torsion if these cantilevers are not resisted by what I call a back span, but just coming out sideways, because that does require the torsional resistance of that supporting beam, and you would need to do that. So it's not always the case, but in here you have this facility. Now you'll also notice here that we're taking portions, but we've actually glued these two together, and what we've done to glue these two together is we've actually said let's make these two into what we call a super member, and it glues those together so they're treated as one. Makes your reinforcement design a lot simpler than having this little small cantilever with its end steel and its support steel. No, just run it straight through and it'll look after itself. What I could actually do is I could actually take this, and I could take this run and add that to that, so that it's all in the one run. So if I put it into plan view, we should now find that that's now part of that run. And when I come out of super members back to beam design and move away, we now get this as one continuous length for the whole member. that can be useful. Obviously we've got quite a length here, but it's not that long. What is it? 3, 6, 7, about 8 meters. So if I was to redesign that one run, we could get away with just 412s top and bottom, and at the two ends U-bars 412s. So that's made that rebar a lot simpler. Obviously the steel is 6.2 plus 7.2 meters long, which is a reasonable length for a 12, so you might want to cut it up from that point of view or make it over. So you can glue beams together again to make your life simple. So if you look here, we've already done that over here for this longer length, and again it is now working for that longer length. So that's another facility that's very, very useful in the concrete design. Now, having designed all your beams, you can have little options like let's go and check and scan for failure. So run along and it stops at the first failure it finds, and it is to do with the transverse reinforcement cross centers, and it's just saying that we're too far apart in some of these rebars, and we just need to sort that out. So the transverse center of the links is too far, and we need to put another set of links in to sort that out. But it's very small, it's within 25 mil, so I would actually argue that it would be okay in this case and just get on with it. All of this can always obviously be printed out. We can take any of our runs and we can come and we can go export to DXF. So we can take all our beams, and I'm going to have just my beams and load AutoCAD, and hopefully it loads the right version of AutoCAD for me, and I'm going to say export. Yes, it is 2018, my favorite version of AutoCAD. In it comes. And it's just loading up now for us. So there's all my little beams just set in one after the other, and then you can just go and frame them up into pages. So if I go in and look at my little spans, I can see my beams and my bars all detailed up, and all my cross sections and all available to myself. So that's your drawings. You can also then print the schedule that matches that, and off you go, and you produce a schedule that will match that, and there are all your beams all scheduled out. And you can say, well, what's the weight per bar? So there's your bars. We actually used 8 mil bars in some places, hopefully for links, although probably don't want to be using 8s. And you can see that we have a total of 2.68 tons of steel, and we can even see what shapes were used. So if we go to the schedule and look at the shapes, we can see those are the simple shapes we used. There was no torsional links used because we pinned everything, and happily done. Now, one last thing while we're in here before we move on to rafts, and that is, how did we put the loading on this? Well, the simple answer is that we first of all did this as gravity two-way spanning. So we did area loading, two-way spanning, and we then, if we take that off, so we two-way spanned everything. We then went in under loads, and if you look at your not individual member loading but your floor panels, and you'll see all your panels that were done. If you look at the alternate loading groups, that's the bit I wanted, alternate loading groups, you'll see that we've actually said, because I knew where all my supports were, how I wanted it to be, these are all the D1s. So by doing that, we're getting our patterns automatically carrying through. So for here, we've got D1 along here, that'll be D2 and that'll be D1. And likewise here, D1. And then we have the D2s, and we have the D2s as these. So those groups allow us to separate out our loading patterns so we can get all our permutations. And since it's not a flat slab or anything like that, we don't need to do it in two directions with 4 sets of load groups. So that's how you do the patterning. So now the next thing I want to look at is rafts. So normally rafts are used for small domestic work. And if we look at this little L-shaped building, and if we look at the gravity loading that I've applied, we'll see that we have all these loads on. So let's step back. What have we done? First of all, we have created some simple members. So if I turn off the FE elements, there we go, we have this boundary, so we don't need to see the mesh. What we have are all these members, and all I've done is created the bounding members to define the elements. So if I go into modify my surface rather than add, you'll see these are all the members I have created. These are the physical members inside the frame. And it is easier to actually put in little members internally for where you want line loads, because it just makes your life a wee bit easier, although I will show you that you can define line loads and point loads and patch loads anywhere on the surface. So define the surface boundary, that's the simple part. Openings, well, don't have any. Edge supports, this is the key element. We tell it we have a restraint, but we tell it we have a spring stiffness. Now I can also tell it that is compression only. In this case I wouldn't need to, because I'm going to get no tension because it's all gravity down, but I could tell it's compression only. This is the figure that you need to be very, very aware of. What is your subgrade modulus? That is the spring stiffness, the number of kilonewtons to make a meter square compress by 1 meter. So it is a large number, in this case 20,000. And people ask us, where do you get the values? What values do you choose? Well, obviously that is between you and your soils people, but I'll give you a little bit of guidance on that. If I was to go and look at, I found on the web a lovely part of a publication on soils, and it gives you some nice typical values of subgrade modulus, loose sand up to 16,000, so you can see, yes, it is tens of thousands. Dense sand up to 128,000, clays anything up to 80,000 for clay sands, and then when you get into pure clays, you're looking at your bearing capacity. So in reality 20,000 is not an unrealistic choice of subgrade modulus. If you're on the, obviously if you're doing a raft, you wouldn't really be looking at onto sand, you'd be looking at onto some sort of softer clay. So you'd be saying if the values are less than 200, we want to be down lower. So we could come back and say, well, actually it's quite a yucky loose clay, or worse. So I am going to go back and I'm going to set this down to 1 as in 10,000. So I've reduced my subgrade modulus. So that's all I do there, and I've made a compression. The other thing I do need to do is I will need to give it 2 supports, here and here, without a vertical restraint. just so that the structure doesn't move sideways. But since everything is a vertically down load anyway, it'll not have much problem as long as you just put 2 restraints in. So that's your supports. Material thickness, in my case 200. And then finally your loading. So I have 14 loads on this. I have a superimposed dead, some sort of screed or something like that, of 1 kilonewton, because the self weight will be included automatically. I have a 2.5 kilonewton live. I have then a perimeter load of 15 for my external walls. I then have a live load of 5 from first floor and roof, and a dead load of 10 from first floor and roof. Obviously these values aren't that accurate, but 10 and 5 sort of similar, and 8 and 5 on this end. Now internally then here I am supporting double the load, so I have 25 and 13 on this wall, and then we have a little wall that's inside the structure of 15 and 2 other walls. So I was easily able to create those putting in these values. If I go into plan and just zoom this down, if I wanted to actually put a load across from here to here, that's reasonably easy. I want to go in and add a new load. I'm going to tell it that it's a line load, and I will tell it that it is vertically downwards minus 10 kilonewtons. Actually, probably nicer to draw it this way. I'm going to take it off here, and I'm suddenly going to say that this load is going to be from, and in apply mode, from here to here, but nothing happens. What I need to do is get my load points up, and I can see that I've got load points already generated. So my load points, I'm going to say, is from there to there, and apply, and there's my load. So load points are generated automatically every single nodal point that you have, so you can use that to do those. But if I wanted to come along and add in another wall, number 16, and I wanted to do it from, so it copies the values and it creates a new one. So I'm going to put this in at minus 8, so it's different. Take out these 2 values, so it copies the location, and I'm now going to put in a new location. I'm able to actually run along and catch points. Now at the minute I have a very coarse density. What I'm going to do is I am going to set the snap and the grids down to 0.1 and 0.1, so I can move along members quite easily. Just pop this in the plan, and I'm going to say that I want to come along and I want to be out here, and then I want to be over here and over here and over here and over here, and apply. And it's now done that and put that onto the structure for me. Likewise, we can do the same with area loads. So I could say it's an area load, and I could even say it's a varying area load. So those are the load points that define it, but the varying points, so for any patch you just need 3 points to define the location. So if I just draw my load points, I'm just going to make this quite quickly 25, 27, 26. So 25, comma 27, comma 26, and then tell it that it's going from 8 to minus 8, sorry, comma minus 8. So that's still the same, but if I then say, well, actually at 26 it's all the way down to 0, then you will see that you actually end up with this load, and this value here will be even higher than 8, but these 2 points across the axes that we defined it on are the ones that are defining this patch. And obviously the scale is quite large in that case, and you may want to pull that down a wee bit to make it a wee bit more intrinsic, but it's showing you where the axis points are and how it's applied. So that's a patch load, and so you've patch loads your line loads that are all done on the structure very simply. An FE structure. So let's go and analyze this. Static. Space frame, it's always space frame. So let's go into our results, graphical, and it's shell elements. So we're now in the shell elements and we're seeing big errors. And what we're seeing here is the errors. The error overall is not very bad. It's only 2.6, and on the fine elements that's not a big problem. But in reality, we would like to see a lot less. I like to see a lot of blue and a lot less. So what I'm going to do is I'm going to come out. I'm going to do 2 things. I'm going to go to analysis, and I'm going to go to the global meshing option. So global meshing at the minute is 1 meter. I'm going to go put in 0.25 of a meter, so a quarter of a meter. And then I'm going to tell it to give me a local mesh intensity for this node here. So in apply, I'm going to do this node. So for this node, which was the one that the error was climbing around, I'm going to go to 0.1 with an influence of a meter. So around this area we'll have a higher intensity of mesh, and go. So let's just go and look at results again. It'll automatically remesh and space frame and into elements, and we'll now see we've got a far finer degree of meshing and a lot less area that's got any high errors, and 1-2% error in FEA is not a problem. So we now know we've got a frame that looks about right. So let's look at our results. Membranes we're not interested in. Moments, we can see moments coming across from left to right in the X, as you would expect. And looking at the y-axis, then coming across in that a bit lesser because it's more inclined to span that way in this example. And then you have max and minimum values or principal, and the reason for that is because obviously the moment is at 2 different angles, and you can say, well, what is the maximum of those 2? And you can now see where the maximums of all those are, and there's a little bit of increase high moment around this, which you will in reality ignore because it's so small of an area. But these are not that important, they're more academic. What you're interested in is the wood and armor moments. So MRX, put it in the plan, and you will see that you're getting an MRX spanning from left to right, going from hugging to sagging to hugging to sagging to hugging again. Or since it's a raft, it's actually the other way around. This is the hugging because it's on the tops, the steel's on the top that's actually in flexure, but that's not that important other than to know where to put them. The y-axes aren't that significant. So there's your wooden armor moments, and you could use those moments and those values, and you would use those values there, and I can just say give me some values, and I can say, oh, we're round about 10, 15 is our maximum sagging moment, even 20, and you would design for that moment across there, and you can say, well, what's the worst in here, and it's around 30. Well, 30 here exactly. So you design for that 30 kilonewtons per kilonewton meters per meter run, and you design for it and happy. We give you the tools to do that automatically because we allow you to say what is the area reinforcement. So you can see what is the top steel. So we're needing up to 400 mil, so we're going to need a wee bit bigger than the 393. So if I go down to a low number of zones and I click in here and I want to add in after 393s, I would see, well, actually I would either pull the 12s down to 440 in there. I didn't get the 440. I clicked on the wrong one. There we go. And just apply. And we now have this all the way up. And we can see that in here we need the heavy reinforcement. In here the 393 will do. So a little bit of extra reinforcement is required in this area on the top. So just close that and scroll up, and that's the top X. The top Y is a bit more inert, so a 10s at 200 will work fine. You could probably get away with 8s at 200 if you want. The Y-axis, there is a little bit, and it's all very concentrated over these line loads on this surface. So you can see here you're up to 300 just in this one corner. So in my case, I would say, well, really 8s at 200 will be satisfactory. I might as well 252 mesh. However, in this zone we would just put some additional reinforcement in to make sure that there's no cracking around that corner, and then we would move to the bottom in the other direction, and we'll see that again there's nothing other than this one area. Now, what we've only been looking at is the ultimate. The serviceability is not important, but the serviceability can allow us to see things like what is the Y displacement. So here we go, we can see what is our serviceability Y displacements. Under the wall here, this is moving all the way down by 1.1 millimeters, which is no movement whatsoever. So our 10,000 kilonewton meter subgrade modulus is giving us reasonable answers, and up to 0.5 mil in these areas. So we can see we're getting very little movement, and that keeps us happy in our design under live only. You might want to look at just the ultimate values, because obviously we could jump back and do a dead plus live service case to get those values as well. Now, as well as that, you also had the facility of creating sections through the diagrams, and we can say let's do a section line. So let's do a line that is a section line, and I'm just wondering where is the first one. They've all been deleted because I was playing with this file. So let's take this first one, and we'll say this first one goes as a MRX, and we'll take it from here across to here and apply, and we'll see that it's giving us our moments, and obviously we need to do a wee bit of scaling on this. Our scales are a wee bit too tight, other direction, and I should expect the reversal of a normal one because it's an uplift from the, and that gives us a very good confirmation of what's happening. And if you went to the next one and shows the next one, you could say, well, let's do it from that one to that one and apply. So it's actually locking into exact nodes and being accurate for you and everything. So we're picking basic nodes, so we can actually tell it, well, actually no, let's go here and put this right here, and it's node there, and it's this node right here, and apply, and it gives us a slightly more accurate. We've also here got something called strip averaging. So rather than just the value here, over across here is always very, very important, because if I look at the values here, we will see in here we're getting 26 because of this point here. If I was to take out the strip averaging, you'll see that's changed because of us. Now, if I put it in, I can see that I'm actually a wee bit out in this, so I'm going to take this down to there and apply. So it's now gone up, and it's now giving us a moment here of 51, but that's over that very, very tiny distinct point just there, and it's infinitesimally narrow. If I went for a half-meter strip average and apply, it's dropped down to 26, and it's a reason why we don't choose the very, very peak values. We average these things out. And if I went and averaged that down to 1 meter and apply, it's gone to 23. And of course it would get smaller and smaller. So again, that is a decision you need to make as to what your strip average is. So that's a quick run through of a typical raft. Rafts are very powerful because rafts also allow me to do combined footings. And this is no different to what we've done, except we've got two columns, which are two columns. And when I go in and look at the results graphical, in this case, shell elements, and I ask for spring supports, we can see that we're coming down to having 0 all the way along here. So we're actually having it just here, and this is in tension but no value because it's got a compression only. So we've got this whole structure working such, if I went back to line elements and asked for deflection with geometry, you'd see that it's tilting and lifting up on the structure. So very, very clever, very, very powerful, and again that does the job for you. Now you're getting no moments obviously because it's the shells that are important. So if I now go and look at my rebar, I can see I've got top steel here I need, I've got bottom steel there, and I've got bottom steel there and top steel through there. Now one of the things somebody asks is, can we do attached beams? And the simple answer is yes. We could come along and put a member down the middle of that, like a spine to support it, and make that attached. Or we could put edge supports and edge surfaces. And let me think, I'm actually going to go to another file. And then we'll look at the pile caps. And piled slab. Piled slabs, not necessarily rafts, but it gives us a similar idea. This is a piled slab with supports that are not necessarily all the same place. But what I've done in this example, I can come along and let's go to properties, edit surface. So there's my surface. My surface is got a thickness of 300. If I wanted to create an attached beam down here or along here, because this is long spans, I would go to attached beams, and I would say that I want to attach this member, and this member. So do I want to attach it to the center or to the bottom? I want to attach it to the bottom and no additional offset. So if I draw my members in 3D, I now see that I am getting these coming down and dropping down below, and that allows me to model those in the analysis and go through. But the trick here is that in the actual properties of the section for this member, I only give the value that is below the slab. So although it's defined along that centerline value, it is 400 from that point to that point. So it's a 400 drop. So it's a 400 square plus the 300 above. So you can see this one, which is not attached, is irrelevant. Any member that's not attached is then lost inside the slab when the FE surface is generated. So just turn off my 3D and that's that done. So rafts are very straightforward, very useful, very handy. The other program that we have is for piles. It's a very powerful little program. Here we got a little 2-pile pile cap. The column is eccentric from the beam, the pile cap. Obviously most people would just design this as a simple beam, but doing it as a pile cap does have its advantages using truss analogies and the likes to get a more accurate design. If I was then to go and look at my second example, this is a 4-pile pile cap, and again the column is eccentric. I can then suddenly turn around and say, well, actually I want to create the imposed loading from wind or whatever gives me 120 kilonewton meter moment in both axes, and obviously that's not really going to worry this little very deep. So as I come down, you'll suddenly find I have problems with shear, and if you look at my results, I am looking at the moments and from that proportioning out where the ultimate loads are, and from that back calculating what the design moments were going to be from the summation of the pile loads times their distances from the surface. So it's calculating for each of these piles backwards and finding the worst moments in the MX and the MY to do the design. So it's a very smart and intelligent little program for doing pile caps, and it's very simple and easy to use. EC2, SABs, and the BS. So obviously the old-fashioned BS or the more up-to-date EC. We can also do square piles, so that if we have piles that are square, it'll allow a bit more on the edges to ensure that if the piles aren't set square, that they don't suddenly stick out. So it creates a circumscribed circle around the pile cap rather than inscribed. As you can see, so we get the same arrangement. And also, what else can we do? So let's looking at pile diameters, the working loads, the number of piles, and our loading. The loading as well, you need to understand when we're working with the Euro codes, we also have this accompanying imposed load. So if we were dealing with a dead plus live plus wind condition, we would have an accompanying imposed load that has a different load factor, such that if you wanted to say that the wind was giving us a 500, well, since it's possibly detrimental, you might actually want to put it in a 1.5 rather than 1.05 if it's giving us those. So you have all the facilities you want to. So putting in a physical load, you can see now the shear perimeter is unhappy and it's giving us a warning on our shear perimeter. Due to the enhancement, we're at 1.33, 30% overstressing in our shear. So what do? Very simply, we can add more rebar in the right axis, which isn't always that beneficial, or we make the foundation deeper. As you can see, it goes up very quickly, because as you get your thicker pile cap, your perimeters are being pushed out, which makes them longer and obviously deeper at the same time, so you're getting a squared function on that increase in capacity. Again, these are very simply exported into DXF and scheduled. Somebody's asking, can you do this as a beam? Let's get back to that first example. Example 1. Example 1 is being designed as a beam. It's looking at strut and tie and beam theory, and it's checking for both of those. So what we need, because at the minute I believe possibly the design method is the maximum, whereas I can say no, let's go for a beam theory. And it's now turning around and saying that, well, actually the strut angle is too large for beam theory, so it's saying no, 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 you should be in this case asking for strut and tie rather than beam theory. So it is again holding your hand. So if I go back to beam theory and I take this and I reduce, so we're not getting a beam theory warning, we're just getting our deep beam design. So although it's a beam, it's still a deep beam due to its span. So it is again checking it using the deep beam theories. The centers of the piles is determined as pile diameter. So if you said let's make this a wider 5 pile cap, a 5 piles apart pile cap, which is quite large, then you might find that we're no longer worried about deep beam theory, just beam theory, and beam theory itself is going to still make you have far bigger reinforcement as you would expect for such a shallow and long structure. So yes, you can go for long pile caps, you can go for beams, but it will always hold your hand and tell you when it is not suitable for design. So if this was required, obviously what you would be looking at doing is putting in an awful lot more reinforcement and seeing if that improves it. So we're still, and it's not really the bending that's the problem, it is the shear. As you can see, if we went up to 40mm bars, we have no bending problem, but we still have this shear problem. We just don't have the shear plane for doing that. And it is a pile cap rather than a beam check, so it's not going to be looking at your side steel as links at this moment in time. So if that was the case, then I would go and do it as a physical beam rather than try and mess around and try and be overly smart with it in that respect. So that's a run through the different programs available for doing concrete foundations. Okay, so somebody's asking, how exactly did I redistribute the moments? The redistribution is done at design time. So let's see, ground beam. No, I don't want that ground beam. Take this one. What you're doing is you're going into your design, into your concrete design, and then you're going into the redistribution area. So what you're saying is what you want the distribution to be. So I want to have, say, a 20% distribution, and then you click where you want to apply that. So you could apply it there and there, and then you could say let's have only a 10% on these inner values. And that's how simple it is to apply the redistribution. You actually set the value and then you apply it for you. So it's not that difficult to apply. And then once you've done it, you don't see any changes here until you go back to here and start to look at different beams. Now, looking at the diagram, you have 3 curves. You have the elastic curve, that's the blue here, the lighter blue. You then have what we call the shear drag, that's the increase due to the shearing. Because this isn't a bending moment diagram, this is a FT capacity diagram. So, and in fact, the grey is the elastic, the blue is the redistributed down, and then it's dragged back up again due to the shear to give you that. So you get the 3 values, and obviously the shear drag can't go any bigger than the original, so it's actually truncated over here and over here as well. So that's what those diagrams are. Where can you set U-bars? Okay, very good question. By default, these are just random bars, and you can play around with them. One of the settings you have in here is a setting for the curtailment and the methods of curtailment, and one of them says end as U-bars. Now what actually happens is that when I tick that and say OK, it says U-bar here, but these two bars are still available separately because you want to be able to change them separately if you need to do so for design. And it would only be at printing out time or at exporting time that I would say, hold on, these are the same diameter numbers, it's a U-bar. Can you do elastic support reactions? Yes, you can. Now, if I went in here and I went to my restraints, I have my static supports, but I also have both springs and settlements. So if I went to spring supports, I could turn around and I could say, well, actually this support here has a spring stiffness of, is that enough zeros? It is 10,000 kilonewtons per meter square. Okay, so assuming 1 meter of support, and it's 10,000. But that's not going to do anything if the actual physical support is still on that. So I need to take that off. Otherwise the reaction would be physical. And I'm going to go to a third one, and I'm actually going to put a settlement, and I'm going to take this support and I'm going to drag it down. So SY by minus 50 mil. So I'm pulling this one down by 50 mil and I'm making this one to spring. So that's the theory. Analyze it. Static supports and plane frame. So let's look at our results, and it is, first of all, it's really just a graphical. And you can see due to the spring this is going down too much. Now this is still a hard support, but it's been pulled down. Yeah, so this has gone down and this has gone down. Those two are rigid and those are rigid. So what are our values? So if you go there and ask to show nodal Y displacements, that's the 50 mil that I had allowed for as a settlement, and this is the spring, the resultant from that spring of 23 mil. So we can do both of those in here for you. If you wanted to do a beam that was got a spring support underneath it, you would really need to introduce a series of little supports at every meter with the spring stiffness, and then analyze it as a super beam to do that. Or you could try and do it as a finite element. Either way would actually do it. Personally, I'd probably do it this way, as being split up into beams at 1 meter intervals and having the spring stiffness on each of them. And remember to put the two end ones, if it's every meter, put the two end ones as half the value, because you're only catching half the load and half the spring stiffness. Where does the bar bedding schedule come from? The bar bedding schedule comes from the program, without being rude. The frame analysis program in concrete design has the option, and obviously with our new settlements we're getting new problems. Let's just redesign all this. And you'll see we're needing bigger bars here because of this settlement, and I'm going to take these bars and I'm just going to stretch them a bit further, and now it's satisfactory. So export and schedule, and there you go. and it would again give you the schedule for that. And oh, SABs? No, 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 no. 8666 and schedule, and it's going to give you the bar schedule for that beam as designed. And likewise, inside the Pile Cap program, you have the schedule. So if you went to export, you could print the schedule, and you could choose which ones you want to print the schedule for, and schedule. And there's your 3 piles. Obviously, the third one is a triangular 3-pile arrangement, and it's giving you all the varying bars to number each top and bottoms on those. So the schedule is available directly for both of those for your usage in the programs. So ladies and gentlemen, I have covered this. We've had quite a large turnout from around the world today. I noticed I had people from all the way from Australia and Africa all the way up to Zambia. I think it was Zambia. We had a client. So from A to Z. All the best and thank you very much. Goodbye.